Hello friends, welcome to our YouTube channel. We have learned that an electrical network is called a two-port network when it comprises of one input port and one output port. We can describe a two-port network in 6 manners. Each method uses a set of 4 parameters. As all the sets of parameters describe the same two-port network, there exist definite relationships between them. Today we shall establish interrelationships between inverse hybrid parameters and the other sets of parameters. Like hybrid parameters, inverse hybrid parameters are widely used in the field of electronics. They are often used to develop small signal models of transistors. They give us directly the voltage gain, current gain, input-output impedances of amplifiers. Let us recall how we have used inverse hybrid parameters, or simply called G parameters, to describe a two-port network. While using G parameters, we consider input port current I1 and output port voltage V2 as dependent variables and input port voltage V1 and output port current I2 as independent variables. The linear equations used in this case are I1 equals to G11V1 plus G12I2 and V2 equals to G21V1 plus G22I2. These two equations may be written in matrix form as follows. Matrix of I1 V2 equals to matrix of G11, G12, G21, G22 into matrix of V1, I2. Here the elements G11, G12, G21, G22 are known as inverse hybrid parameters, or simply called G parameters. Some of them are measured by open circuit test and some of them are determined by short circuit test. They have mixed type dimensions. In this case, we express I1 and V2 in terms of V1 and I2. That is the reverse case of hybrid parameters, and that is why they are known as inverse hybrid parameters. Let us first establish interrelationships between G parameters and Z parameters. When we describe a two-port network using Z parameters, we express the port voltages V1 and V2 in terms of port currents I1 and I2. The linear equations used in this case are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Now rearranging the equation number 1, we get I1 equals to 1 upon Z11 times V1 minus Z12 by Z11 times I2. Now using this expression from equation number 2, we can write V2 equals to Z21 times 1 upon Z11 times V1 minus Z12 by Z11 times I2 plus Z22 times I2. Now rearranging this equation, we get V2 equals to Z21 by Z11 times V1 plus Z11 Z22 minus Z12 Z21 divided by Z11 times I2. When we describe a two-port network using G parameters, the linear equations used are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. Now comparing the expressions of I1, we get G11 equals to 1 upon Z11 and G12 equals to minus Z12 by Z11. Now comparing the expressions of V2 we get G21 equals to Z21 by Z11 and G22 equals to delta Z by Z11, where delta Z equals to Z11 Z22 minus Z12 Z21. Now we have expressed our G parameters in terms of Z parameters. Now let us establish interrelationships between G parameters and Y parameters. When we describe a two-port network using Y parameters, we express the port currents I1 and I2 in terms of port voltages V1 and V2. The linear equations used in this case are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. By rearranging equation number 2 we get V2 equals to minus Y21 by Y22 times V1 plus 1 upon Y22 times I2. By using this expression from equation number 1, we get I1 equals to Y11 V1 plus Y12 times minus Y21 by Y22 V1 plus 1 upon Y22 I2. Rearranging this equation, we can write I1 equals to Y11 Y22 minus Y12 Y21 divided by Y22 times V1 plus Y12 by Y22 times I2. When we describe a two-port network using G parameters, the linear equations used are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. Comparing the expressions of I1, we get G11 equals to delta Y by Y22, where delta Y equals to Y11 Y22 minus Y12 Y21 and G12 equals to Y12 divided by Y22. Now comparing the expressions of V2, we get G21 equals to minus Y21 by Y22 and G22 equals to 1 upon Y22. Now we have expressed the G parameters in terms of Y parameters. Now let us express G parameters in terms of transmission parameters. When we describe our two-port network using transmission parameters, we express the input port variables V1 and I1 in terms of output port variables V2 and I2. The linear equations used in this case are V1 equals to AV2 minus VI2 and I1 equals to CV2 minus DI2. Now rearranging the equation number 1, we get V2 equals to 1 upon A V1 plus V by A I2. Now using this expression from equation number 2, we get I1 equals to C times 1 upon A V1 plus V by A I2 minus D times I2. By rearranging this equation, we get I1 equals to C by A times V1 minus AD minus BC divided by A times I2. When we describe a two-port network using G parameters, the linear equations used are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. Comparing the expressions for I1, we get G11 equals to C by A and G12 equals to minus delta T by A, where delta T equals to AD minus BC. Now comparing the expressions for V2, we get G21 equals to 1 upon A and G22 equals to V by A. Now we have expressed the G parameters in terms of transmission parameters. Now let us establish interrelationships between G parameters and inverse transmission parameters, or simply called T dash parameters. When we describe our two-port network using T dash parameters, we express the output port variables V2 and I2 in terms of input port variables V1 and I1. The linear equations used in this case are V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. Now rearranging the equation number 2, we get I1 equals to C dash by D dash times V1 minus 1 upon D dash times I2. Now using this expression from equation number 1, we get V2 equals to A dash times V1 minus B dash times C dash by D dash times V1 minus 1 upon D dash times I2. Now rearranging this equation, we can write V2 equals to A dash D dash minus B dash C dash divided by D dash times V1 plus B dash by D dash times I2. When we describe our two-port network using G parameters, the linear equations used are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. Now comparing the expressions of I1, we get G11 equals to C dash by D dash and G12 equals to minus 1 upon D dash. Now Comparing the expressions of V2, we get G21 equals to delta T dash by D dash, where delta T dash equals to A dash D dash minus B dash C dash, and G22 equals to B dash by D dash. Now we have expressed G parameters in terms of T dash parameters. Now let us derive interrelationships between inverse hybrid parameters and hybrid parameters. When we describe a two-port network using hybrid parameters, we express input port voltage V1 and output port current I2 in terms of input port current I1 and output port voltage V2. The linear equations used in this case are V1 equals to H11I1 plus H12 V2 and I2 equals to H21I1 plus H22 V2. These two linear equations may be written in matrix form as follows. Matrix of V1 I2 equals to matrix of H11 H12 H21 H22 into matrix of I1 V2, or matrix of I1 V2 equals to inverse matrix of H11 H12 H21 H22 into matrix of V1 I2. Or we can write matrix of I1 V2 equals to 1 upon delta H into matrix of H22 minus H12 minus H21 H11 into matrix of V1 I2, where delta H equals to H11 H22 minus H12 H21. When we describe a two-port network using G parameters, the linear equations used are written in matrix form as follows. Matrix of I1 V2 equals to matrix of G11 G12 G21 G22 into matrix of V1 I2. By comparing these two sets of equations, we get G11 equals to H22 by delta H and G12 equals to minus H12 by delta H. G21 equals to minus H21 by delta H and G22 equals to H11 by delta H. Now we have obtained G parameters in terms of hybrid parameters. Now let us solve a couple of numerical problems to have hands-on practice on implementation of the interrelationships developed so far. In this problem, the H parameters for a two-port network are given as H11 equals to 2 by 3 ohm, H12 equals to 1 upon 3, H21 equals to minus 1 upon 3, and H22 equals to 2/3 mho. We have to determine inverse hybrid parameters using interrelationships. We know for hybrid parameters delta H equals to H11, H22 minus H12, H21. Now putting the values we get 2/3 into 2/3 minus 1/3 into minus of 1/3 equals to 5 by 9. Now let us use the interrelationships. We know G11 equals to H22 by delta H. Therefore 2/3 divided by 5 by 9 equals to 6 by 5 mho. Now G12 equals to minus H12 by delta H. Putting the values we get minus 1/3 divided by 5 by 9 equals to minus 3 by 5. G21 equals to minus H21 divided by delta H. Putting the values we get minus of minus 1/3 divided by 5 by 9, that is equal to 3 by 5. Now G22 equals to H11 by delta H, that is equal to 2/3 divided by 5 by 9, that is equal to 6 by 5 ohm. In this problem, the Z parameters for a two-port network are given as Z11 equals to 14 by 5 ohm, Z12 equals to 2 by 5 ohm, Z21 equals to 2 by 5 ohm, and Z22 equals to 6 by 5 ohm. We have to determine inverse hybrid parameters using interrelationships. We know for Z parameters delta Z equals to Z11, Z22 minus Z12, Z21. Putting the values we get delta Z equals to 16 by 5. Now let us use the interrelationships to find inverse hybrid parameters. G11 equals to 1 upon Z11, that is equal to 5 by 14 mho. G12 equals to minus Z12 by Z11, that is equal to minus 1 by 7. G21 equals to Z21 divided by Z11, that is equal to 1 by 7. G22 equals to delta Z by Z11, that is equal to 8 by 7 ohm. So today we have learned how to express inverse hybrid parameters in terms of other sets of parameters. With the help of these interrelationships, we can easily find inverse hybrid parameters when we have another set of parameters readily available. Finally, we have solved a couple of numerical problems to have hands-on practice on implementation of these interrelationships. So that's all I have for you today. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.